who are going to talk about We Built a Clock in Python. Round of applause for Emma and Leila. Thank you.
So, hi everyone, I'm Leila and she's Emma. You can find us on Twitter, GitHub. We also have a website on the blog, but I will give you all the link at the end of the talk. And today we will talk to you about, actually, we made 2 clocks in Python. But first, let's introduce ourselves with more details. So, who are we?
I'm Emma, and this is my plushie dog, Noel. And I'm the co-founder of Levit. For everyone who was not in the talk before, you might have heard of me because of one of those 2 libraries, your schema adapter or Ember CLI Creditis. Those libraries allow you to build complex forms and do complex data management through Django, Django REST Framework, and Ember.js.
And I'm one of the co-founders of Levit as well. I started to code in 2014, only with Python, and mostly Django. And 2 years ago, I started to work with Ember.js as well. 2 years ago, I also heard about microbits for the first time at PyCon UK, and since I love to play with them, and I love to play also with electronic and circuit Python. Oh yes, and this little dog is my plushie, debugger plushie, and his name is Sam. He got a surgery last night during a manual activity workshop.
By our chair, who was nice enough to do that.
And today he got his first badge. So, yeah. So, why we made this little clock? Because it's our first one. A few months ago, a clock broke just like this one, there, just like on the floor. And we wanted a new one with a few basic requirements. Segment had to be blue, and the time had to be visible when it was dark. And after searching a lot and only finding red or green ones, we finally decided to make it ourselves. So what did we use? To make this clock, we used a trinket M0 from Adafruit, an RTC module, and a blue quad 7-segment display and its driver. We also used a breadboard and a lot of wires.
Thank you. So she just said that we used a quad 7-segment display. What is that? Well, it's a quad means that there's 4 numbers. And 7-segment display is usually what you use to display what's called as digital numbers, like this 8 here. And there's 7 segments, 3 horizontal ones and 4 vertical ones. So that's a quad 7-segment display. It's a mouthful, but it's something that we have all seen at some point. She also mentioned an RTC module. So RTC stands for real-time clock. Everything that has a crystal is basically able to keep time, to count the time that goes by the number of ticks of the crystal. But an MCU, the processor in your computer, all that is not really precise. And so when you want to keep precise time, you usually use an RTC module. The RTC module also is able to keep time as a datetime object, a struct time in Python. And depending on the kind of module that you buy, they might have some advanced features like being able to keep several times at once, or do timers, or have an alarm stored as well, depending on the model you get. Some of those also are able to store an offset, because precise as it may be, an RTC module is sensitive to temperature and things like that. And so they might they might go off course by maybe 1 second a day or something like that. And so depending on the model, you can store that offset and say every day go back 1 second. Oops.
So let's talk a little bit about the plan. As you can see, we used a medium and a small breadboard. On the top, it's a circuit without a component. And on the bottom, this little thing in the middle is a 3.3 volt to 5 volt one-way logic converter, because the datasheet said the display driver needed a 5 volt signal and the trinket outputs a 3.3 volt signal. But in fact, we should have used a two-way logic converter to this to work. So, and we didn't have one. At the end, it turns out both the RTC and the display driver work fine with a 3.3 volt signal. So we got rid of the logic converter altogether. And at this point, we also decided to use a single medium breadboard. So we had to make a new circuit.
Okay. So now let's talk a little bit about the code. For the ones of you who were in the talk before, I already mentioned the fruit and said that they publish Python drivers, Python modules for all their hardware, and that's really nice. The problem we had with this clock is that there's a driver for the display, a driver for the RTC, and when you load both of them into the M0, you fill up the memory and you don't have any memory left to write your program. So wrong button again, sorry. The first file here is called PFC8523 Lite. PFC8523 is the port number of the RTC, and Lite because we had to write a lighter version of the existing driver. The problem of the provided driver is that it treats the date time as a single time struct at once, and that takes a lot of memory for a little device like that. So we wrote a library that treats date and time bits by bits. It treats the hours, it treats the minutes, and it is able to display the time. We don't need to read the date, except if we want to display or modify the date. So let's not take up some memory to do that. The second file here is the clock, clock.py. This is the main file which handles showing the time, which handles what happens if you click a button. Does it add a minute? Does it add an hour? All that is in clock.py. And finally, utils.py is a set of small utilities to convert things like BCD to decimal. BCD is a way to represent number that's used in electronics. It's binary decade, binary counter decade or something like that. It means that you get a binary value for each digit, which is not the same as having all numbers in binary. The utils.py also has functions to determine if today is winter or summer as far as daylight saving time is concerned, because this clock changes time automatically when it's daylight saving time. This is a simplified version of the PCF8523 Lite. So as I'm not sure you can read it from the back, but it's not a big deal. But this is not Python, as most of us are used to write it. If you're a web developer, data scientist, or even DevOps person, you won't do this. Here in the read method, what we do is that we write some value in a register, and that way we can read another value from another register. This is very much what you would have done in assembly language or something like that, except here we do it in Python. It's a bit easier in Python, but this is still something that you usually don't want to do. Same thing for writing. We just write values directly to the registry. This is what it costs to have a lighter version of the library. You have to address the registers directly. But it works.
Yes, now it's work. Can we show the camera?
Can we do what?
See the camera?
Yes, can we see the camera, please? The small.
Yes.
So this is our small clock. It works. It's 2 minutes slow because we didn't exactly know the time when we set it.
Thank you.
So yes, this is all we had to show, but we needed people in the back to see.
Okay. So, after our
Wait.
What? Oh,
A few seconds before
Sorry.
it comes back. Good.
well, after our success with the small clock, I said at the end of my lightning talks at DjangoCon Europe this year that the next step was to do a bigger one. And as you can see here, it's a success as well. Everyone?
Can everyone see the big clock from the back?
Yes.
Yes.
Okay, great.
This is a big clock. Yeah, you can go back
Yes.
to the
Thank you.
slide.
So, every year. After DjangoCon, I was very motivated to finish this project, and giving a talk at PyCon UK was a big source of motivation to finish it. So I submitted a proposal, and fortunately, it was accepted. But what was the challenge with this second clock? Because we already have one. So the challenge with the second clock was to make it with a maximum of upcycled things. So all the cardboard and all connectors are upcycled. The cardboard comes from some wine or milk boxes, and connectors come from old computer, power supply, and CD-ROM drives. And what exactly did I use? Well, I used a lot of things to make it. First, I used a lot of cardboard and a lot of wires. I also used an HCBC M4, and remember, for the first clock, we used a trinket M0. But at the end, we were happy to have more memory available the second time around. I also used an RGC, a breadboard, and some other little things like Neopixels, paint, and glue.
Okay, so she just said that we used Neopixels. So for the ones of you who don't know what Neopixels are LEDs. They are RGB LEDs, sometimes RGBW. W stands for white, and they are small LEDs, and usually they come in. That was that button today. Usually they come in a strand like this, and they are all addressable from one single wire. So you can say, turn on the 5th pixel and turn it on blue, and things like that. This is a close-up with the Neopixels. You can see there are actually 3 LEDs in this one. And so by mixing red, green, and blue, like on the screen, you get a different color. On that strand on the left, you can see that you see dots. You don't see a line of continuous colors. You see dots. And so that was a problem for a clock, because with the size of the clock, maybe we needed 4 or 5 pixels to create one segment, but that would have been 4 or 5 dots, not a line. And so if you try to Google diffusing LEDs, you will be surprised by the number of ways that you can diffuse the light from a LED. You can use ping pong balls, you can use tissue paper, you can use a lot of things. What we decided to use was a light box. What is a light box? Well, in this case, it's a lot of cardboard and glue. A light box is basically each of these shapes, each of these triangles, as well as the diamond in the middle, is a light box. A light box is a box where you have a light that will not shine directly towards your target, but will shine inside the box, and the light will reflect and bounce inside the box and will get out of the opening. So here we got our opening, and there's only one light that creates the light that you see because it's reflected inside the box.
So how I built it? Well, in fact, it's quite simple. I started by drawing all the elements of each number on cardboard, and I saw on this picture that it's missing one of them because we need three of those big bars, not two. And then I cut them, and my finger a little bit as well. And after that, I put them together, the cardboard pieces, not my finger. And then I used 33 Neopixels, 8 by numbers. Yes, I know, 8 times 4 is 32. But unfortunately, I killed one in the process. And then I make the circuit and connections, and that's it. But that is in theory. But in real, it's a little more complicated than that. And why it's more complicated? Because of the size of the separators. That's what's not easy. Of course, it just looks like a bit of math to compute their lengths from the angles. But we are talking about cardboard, thick cardboard. In the end, it's easier to just guess. But now I'm talking about it. I think the most complicated part of the process was to have the same size of each element at the beginning and at the end after cutting them, because sometimes while cutting them, the knife just would slip. A little bit about the plan of this one. We used the same program to make the plan of the two clocks. And as you can see, we used a single medium breadboard, and we added 3 buttons. What to change hours, one to change means, and one to change mode. You wanted to
No, it's okay.
No, okay. Also, each time we draw a plan, we try to not cross wire on it, because to do it more aesthetic. It's also useful if we want to use a regular circuit board instead of perma protoboards.
Okay, so she just mentioned that we use the same program to make the plan for the first clock and the second clock. What she didn't say is what program is that. So we used Fritzing, which is a program that allows you to make these kinds of plans. And now, if you talk to any electrical or electronics engineer, they will tell you this is not a proper plan. You should make schematics. Well, they're probably mostly right for as long as their work is concerned, but the problem with schematics is that they are not representative of the real circuits. They don't match the connection where they are. They just show you the components, how each component is connected to each other, and it's just arranged so that it can fit on a piece of paper. Now with Fritzing, you have the real thing. You have your breadboard that you're using and exactly where you're going to put the wires, and depending on what board you're using, you can even test those circuits and try to put 5 volts on a wire and see a light up sometimes. So this is easier for somebody who is not a professional electronics engineer or something. If you're working with skids, this will be much better than schematics. And I'm not an electrical engineer, so it's much easier for me too. So now a little bit about the code on this clock. So you might have heard that Leila mentioned that this time we used an M4 instead of an M0. I see some people trying to read the code. You're just going to kill your eyes, don't. She mentioned that we use an M4 instead of an M0. The main difference between an M4 and an M0 is that an M4 has a lot more RAM available. So this time we didn't have to write a light driver for the RTC. We could just load everything datetime at a single time. The other major difference is that now we're using Neopixels. So we had to write a lot of if statements to say if you want to show a 1, you have to light up these 2 pixels. If you want to show a 2, you have to light up these 5 pixels. So this is the 2 main differences between the 2 codes of the clock. 1, we don't need to care about memory as much. And 2, we have to light LEDs instead of 7-segment display. A 7-segment display, you can just send a number, it will show up. Here we have to tell it which LEDs it needs to display. Back to you.
Yes, thank you. How long did it take? Well, I'm not totally sure about it because I couldn't work on it every day. But I think I spent about a day of work to make all the numbers, then a few days to draw and make circuit, and then about half an hour to write the code. The most complicated part was to do all connection between each number because I used all connectors and some of them was already cut. So I had to find a way to connect them with the others. And now it works. We have another fully functional clock. Thank you.
Okay, thank you very much, Emma and Leila. We do have time for some questions, so I shall come just right here.
Thank you. I didn't exactly understand the shapes that you made to make the numbers in the big clock. Can you maybe point a bit to the clock and
Yes, let's
and
go
explain?
back to this. So it was supposed to look more regular than this. Basically, there are 2 axes so that you have triangles on all the external sides, and there's one big diamond here in the middle. And so then the cover comes over it with the holes for the numbers. So here, this, you see here, this is the drawing of the segment. This is the hole that's in the cover.
Okay, so
And
it's
so there's an X here, so this box is completely separated from the
You can
rest.
saw it.
It's supposed to be a triangle, but as she said, when cutting cardboard, you sometimes slip and it's thick and you don't get the right length, so it's not exactly a triangle.
maybe I understand. So do the divisions stop the light leaking from one segment?
Yes,
Okay, brilliant.
exactly.
Thank you.
Hi. So I usually sit much higher in the stack. So this was fascinating to me, and both of you are awesome. I was wondering, how did you figure out that the date time was causing the memory problems? Do you remember?
Yes, because this is Python, you have access to the REPL. And so when things were not working, I went into the REPL, I loaded one driver, tried it, used it, displayed numbers, it worked. I restarted the thing, I loaded the driver for the clock, was able to load things and load the date, change the time, it was working. But then when I loaded the 2 together, I think I got a pretty explicit error message. I don't remember what exactly. And from the MicroPython module, you can load a function that tells you how much memory you have left. So this is what I did, and I looked and I saw, oh, there's no more memory left. Because on the M0, once Python is running, so the chip has 250K of RAM, I believe, or 128K, I don't remember. But what I remember is that once CircuitPython is running, it's been loaded on the chip, there's only 20K of RAM left. So 20K is really not a lot, and the time struct is about 16K.
Okay, does that answer your question? Thank you. Anyone else have any questions? Okay, that's great. Thank you very much. Let's give Emma a round.